Oh, I'm live. Okay.
Okay. Hello, everyone. I'm David. I'm also teaching this class. And today, I want to just briefly reintroduce the course from my own perspective. So Nelson did a great job on day 1 and day 2.
Wait, sorry.
And,
I'm just gonna stop
oops,
you. I don't think. Hang on. This is actually coming through. What just happened?
man, things.
Here, I'll let you know when.
Oh, very janky.
Yeah.
Yeah.
This just keeps. Okay, I'm gonna bring it closer this way then. That's not gonna stay on like that. Okay, I think we're back.
They heard nothing, or they heard everything, or what?
I'll let you know. Start over, but I'll let you know when.
Sorry, guys.
Okay.
Okay, hi, I'm David. I'm also teaching this class, and it's day 3 of the class, and Nelson's done a great job so far, but I wanted to kind of reintroduce what this class is about from my perspective. And so for a long time, I have just wanted to be able to talk about the things that I see around me in math as much as possible, just so I could have some accounting system for things around me, right? So I wanted to understand basically communication, and so I started by thinking about databases way back 15 years ago, thinking that we're all kind of databases with schemas for arranging knowledge and then data for like examples. And I thought about data migration, which is how you send information from one schema to another. But then when I was working with some companies, like they were very interested in processes, and processes didn't really work that well from a data perspective. So I started thinking about dynamical systems. And that's what we'll be talking about today, are dynamical systems. And I don't know if we'll get to wiring diagrams today, but we'll get to it either today or tomorrow. And so they're little dynamical systems that talk to each other by sending them each other information. But I really wanted my dynamical systems, when they're talking to each other, to be able to change their wiring pattern, because we do that all the time. We weren't sending information to each other before this class started, and now we are. And so I wanted the internal states of me and you, the people who joined this class in order to come together, to be able to determine, based on those internal states, whether the things were wired together or not. And that's when I came to Poly, which basically not only is good at this sort of thing where wiring diagrams can jigger themselves, but also very surprisingly has databases and data migration functors built in. So for me, it's just a really rich environment where all the things that I've tried to say kind of come together, and that's why I'm excited about this class. And so today, I'll be talking about dynamical systems, which are machines that take input, update their state, and give output. Okay, so I wanted to start by reminding you what a map of polynomial functors is. So if you have 2 different polynomial functors, p and q, then what is a map phi from p to q in Poly? And I wrote it here, which the camera may or may not be able to see easily. But what it says is that a map from P to, so there's different representations I've drawn. A map from P to Q starts with a map, this is a scribble, okay. It's a map from P of 1, the positions of P, to the positions of Q. And then for every direction there, it's a choice of map back. So it's a choice of direction back here. So I've written it in several different forms, and it might be a little hard to see, but hopefully it's good enough. So one way we might write it later on in the course, because it becomes convenient, especially for what are called comonoids and other things, is by just abstracting these things into just single boxes. So this will be called like a poly box. So it's got P of 1 written here, and P of blank written there, and Q of 1 written here, and Q of blank written there. And given and like some blue squares, which are like the user fills in this part, and our morphism phi is supposed to fill in the data. So if you told me you defined phi from P to Q, and a user came in and filled in I, your job would be to tell me what phi of it is. And if they then filled in E, a direction there, your job would be to fill in a direction here. So I wrote it again here. Phi of, so we might say, I think Nelson defined it this way. He said phi of 1 takes the positions of P to the positions of Q. This is the one component of this natural transformation, if you like that. But if you don't like that, that's just a map from positions to positions. And then for each I guess I wrote this here already. For each I in P1, it's like we've already defined some J in Q of 1, so we're kind of saying it twice. It's kind of annoying. It's a little bit hard to write these nicely, but we say there's a phi sharp sub I taking Q bracket phi 1 of I back to P of I. Okay, so that's what's written here. I wrote it twice, I guess. Another way to say it is independent sum, dependent product notation. This one's pretty convenient. You can say it all in one line. It says for all, so you read the pi's as like for alls, and the sigmas as, I will give. So for all I in P1, I will give a J in Q of 1, and for all E in Q of J, the directions there, I will give a direction in P of 1 and stop. Right, so a polymap, finally, one more time, is given by, for each P position, a Q position, and for each Q direction there, a P direction. So you just go forward and back. Okay, so I want to practice by giving you dynamical systems as a special case of this. And the first kind of dynamical systems we'll talk about are called Moore machines. So definition. And A, B, let's say A and B are sets. Let A and B be sets. An A-B Moore machine now, A-B Moore machine, we're supposed to think of it as a machine that takes in A inputs and gives out B outputs. So it consists of three things. One, a set S, which we'll call the elements of states. Two, a function R taking S to the output thing, that's B. So these are outs and these are ins. And three, and this one's going to be called readout. So given a state, we can read out an output. We can read out a B. And then finally, a function that takes an A, and takes a state and gives a B. Oops, and gives a new state. This we'll call update. So U is a function that takes an input A and a state and gives you a new state. And we'll call it initialized. Initialized sounds like a property, but it's actually one more piece of structure if we have provided. So I guess an initialization of this thing is a set, an element S naught in S. So an initialized Moore machine is one of these. Okay, so how can we say this concisely with polynomials? So claim an A-B Moore machine is a map of polynomials, or can be described as a map of polynomials. S, Y to the S, arrow P. Sorry, Moore machine with states S. And it's initialized, and we'll also say why in a second. An initialization is a map Y to Sy to the S. Now you could say, oh, let's compose these. Given this and this, we could compose to get a map from Y to P, and you can. It will be the first position output by this machine. But it won't tell you all the stuff. So it's really these two things, not their composite, that we're really looking at here.
Is P supposed to be a specific?
Ah, thank you. P is a specific polynomial, namely this one, the appropriate one. So it's to b y to the a. Thanks, Evan. Okay, why is a map like this the same thing as an AB Moore machine? Well, a map from sy to the s to by to the a consists of a map from s to b. That's on the positions. So when I write p of 1 here, that's always the positions. Let's plug in 1 into y here. The positions of this is s times 1 to the s, and s times 1 to the s is s. So the positions of this is the coefficient s, and the positions of this one is b times 1 to the a, which is b. So on positions, we're getting a map from s to b, and that's our readout. And then, given an s, it says for each I in P1, so for each S and S, we're getting some kind of map from A. We're getting what we're supposed to call phi sharp sub S, taking A to B. But if for each S and S we have a map from A to B, that's the same thing as A to S. Thanks. So for each element of S, we're supposed to get a map from A to S. Thank you, Sophie. And if for each S and S, we're getting a map from A to S, that's the same thing as a map A to S times A to S. And so we got our two pieces here, the readout and the update from this data. We call these monomials. A monomial is something that's just like of the form AY to B or BY to A or whatever. And maps of monomials, if you've seen lenses before, if you haven't seen lenses before, ignore the next 30 seconds of talking. And if you have seen lenses before, people write things like AB as an object in lens and A prime B prime as another object in lens, and they give a map between these, and they say it's a map from A to A prime and a map from A times B prime to B. And to give a lens map is to give a map from A, Y to the B to A prime, Y to the B prime. So if you like lenses, lenses are the monomials in poly. It's the full subcategory. They have exactly the same maps. They're just restricted to these special maps. So what is a map from Y to SY to the S? Well, for every position of this thing, of which there's only one, we're supposed to give a state. So we give one state. And then for every direction there, we're supposed to give a direction here, but there's only one direction here also. And there's no data there. So given an element of S, we give an element of 1, and we're done. So a map from Y to SY to the S is the initial state. And that's why these are the same thing. Okay, so let me say what a Moore machine does and why it's called, well, why some people might call it a dynamical system. Some people meaning me and anyone else too. So the word dynamical system has a technical meaning in, say, literature or Wikipedia, and this is a more general sort of thing, or it's kind of a different sort of thing in some sense. It's the same in the sense that it does stuff as you give it input. It's like a dynamical system that moves through some state space. It's a different sort of thing in the sense that it doesn't fit the definition there. But we will later give examples of the same sort of formalism, but that does fit the usual definition. It's just I want to be more general about what I mean by dynamics. Okay, so what I was going to say is why you might think of this thing as a dynamical system, a Moore machine. And that is that a Moore machine, I don't know if we need a hyphen there. A Moore machine, an AB Moore machine, sends A streams to B streams. And what that means is, and so maybe we might draw it like this sometimes. It's like a machine. And if you put in a bunch of A's, A0, A1, A2, for as long as you want, then it'll get sent to a stream of B's. And how that works is inductively. So we're going to take an A stream and give a B stream. And the way we do it is, if we have all this data, we would set B n to readout of Sn, first of all. And second of all, we would set S of n plus 1 to be the update of the nth A on the nth state. So we just keep defining new states by plugging in A into our update map and the old S, and just keep updating S and then reading them out. And we've inductively turned one of these into one of these. Or maybe co-inductively, some pedants might say. But in this sort of way. Okay, so we could say a generalized Moore machine is just replace that monomial by a general polynomial. So I want to say how that works. So let's just define, let P be a polynomial. A P Moore machine consists of 1, a set S, and 2, a polymap Sy to the S to P. And then we would say it initialized if we have this thing. So the puzzle that we'll get to later today is what sort of inputs you would give this. So look, okay, that will be the puzzle. Let me try to say what this is. What this says is a P Moore machine which I might call a P dynamical system going forward, would say for every state, I can read out using this sort of, like if you remember what a map of polynomials is. For every state, I can read out a position of P, and for every direction there, I can update the state. So it's almost exactly the same thing. The only difference is that the inputs can change based on the positions. So you could imagine in some states you're in a position where you can't see, and so the inputs coming in are just things you can hear and feel. Whereas in other states you can see, but you can't hear for some reason. And so that's what this P allows you to do, and we'll give a bunch of examples. That's basically all of today is just giving examples of this stuff. But the puzzle that I was alluding to is if we don't know the position until we've updated, like we just get a different position each time and the directions can change, then what should we do with the inputs? It's like we can't just give the same set of inputs. Like the set of directions is changing. So how does the world know what inputs to give us at any given time? And that's the puzzle we'll get to later. And the answer is going to be situations. What's a situation? So I don't know. I like terminology, but I like terminology that fits how I'm thinking of it, so that I can use these words, but be pointing to real mathematical things. So you don't have. It's not philosophy in this. It's not bare philosophy in the sense of not really knowing. You kind of have to put all the pieces together, like what they really meant. And I want to get to the same sort of intuitions a philosopher could get to, but always have math behind it. So that's kind of the goal for me. Okay. So what I was thinking of doing is just giving a bunch of examples of this stuff. So examples. Okay. So example 1. For each example, we'll have a 1 and a 1 prime, and 1 prime will be like a poly version, and 1 will be, or I guess n and n prime, and n will be the kind of monomial version. Okay, so regular languages. So a regular language on alphabet A. So suppose you had some alphabet A. It's a set. Then a regular language consists of a bunch of things. One, oh wait, shoot, not a regular language. Maybe I mean, shoot. The answer is supposed to, okay, let's see, sorry. Maybe I meant a finite state automaton with except states. which is apparently equivalent to a regular language. A regular language is stuff with like, you're allowed to say like star and plus and all sorts of stuff like that. But those are equivalent to a finite. Does anyone know do you know the correct term? A finite state automaton with accept states or something like that?
Yeah, finite state automaton.
A finite state automaton. Thanks, Nelson.
Deterministic.
Deterministic. Sorry for the terrible board work there. A deterministic finite state automaton on alphabet A consists of a set of states, a function, an initial state, three, a function a times s to s, and 4, a subset R subset S of like recognized, or maybe someone might say final states, I think, or accept states. And basically the idea is that this little language machine, you're going to give it letters of your alphabet like H, E, L, L, O, and when it understands something, it'll be in a recognized state. And when it doesn't understand yet, it'll be in just a regular old state. And right, so how would you say this in Poly? That's the question. And the answer is, well, the easy part is we always do that. It's always going to be of the form sy to the s mapping to some p. But the question is, what's the p here? Any guesses? What p would be enough to encode this and no more than this?
Alphabet A, so that needs to be involved, and then the subset will be equivalent to a function into a set of truth values.
Yeah, so Christian says that we're going to have as our inputs elements of the alphabet, and as our outputs whether the state is recognized or not, which is 2. 2 is like true, false. Okay. Okay, so the way you imagine one of these dynamical systems is you have like some states and their readouts, and for every state and every element of A, so let's say question mark means you're unrecognized, and exclamation point means you're recognized. So 2 here is the 2-element set, I got it or I don't get it. And so you'd have all these states, they'd have outputs. This is a way you could write it. These are the outputs, and for every element of A, you give, let's say A is A0, A1. So A0, A1, A0, A1. Every state here will get two outgoing arrows, one for A0, one for A1. And when you get here, you'll say, I got it. Okay, so then the Poly analog of this monomial version of here might be, so what I'm trying to do is like give you imagination to be able to use Poly in your own way. And so what should we have this do more generally than just recognize words? That's a open question. But one thing you could do is you could have this thing listening for a while and like, oh, hello, I get it. And then listening for a while and then understanding. But instead of just understanding, you could have it start talking once it understood what you meant. So as soon as it gets into an accept state, you could say now it can talk in A for a while and then stop. So if you wanted to do that, you would just go from sy to the s to question mark y to the a plus ay. Let me just make sure. Actually, I think I'll do 2 things. I'll have a recognized state, so y plus ay. Okay, so in this thing, I'm going to define a talking dynamical system. I think I can do this. A talking deterministic finite state automaton would be like a subset R of recognized states, a subset T of talking states, and a subset U of unrecognized states, and where R plus T plus U is S. So what it's doing is, it's now, when it's in this recognized state, it says, I recognize this, and then it just starts moving for a while through its own little state space, talking and talking and talking in the alphabet A. And then moves back into here. So S1, S2, S3, S4, S5. So what we'll say is like, so let me give you a map of polynomials from this new sy to the s to this thing. So Nelson mentioned that coproducts in poly are given by just adding polynomials. So we know that sy to the s is actually ry to the s plus ty to the s plus uy to the s, because r plus t plus u is s. So this says that every state is either a recognized state, a talking state, or an unrecognized state. And so to give a map from this to question mark y to the a plus y plus ay, I just have to give a map from each of these pieces to this whole thing. But in fact, I actually arranged it so that I'm just going to give 3 different maps. One to here, one to here, and one to here, or something like that. So let's see what the order is. So I guess it's not quite what I said. I'm going to give a map from unrecognized states to question mark y to the a map from recognized states to y, and a map from talking states to ay. So this one is saying for every unrecognized state, give me the unique position here. And then for every input, give me a new state. Either that new state is a recognized or I'm actually going to have it land either in recognized or unrecognized. But basically for every input, send me either to exclamation point or to, sorry, let me do one last thing to make this a little bit clearer. I don't know if this is any clearer. Maybe I should open it up for questions. This map is just a projection. R plus U is a subset of S. This is R plus U plus T. And this is just projecting off the T stuff. So this part's pretty easy. It's just okay. And then on this part, it's just including that part. This part says, given an unrecognized state, send it to the unique position called question mark. That's what it means to be unrecognized. And for every input, either send it to like I get it, or send it to a new unrecognized state. So we're going to travel around through unrecognized states and finally hit a recognized state. And we'll just consider that to be a state. This one says, given a recognized state, ry to the s. Okay. This again is projection. So given so what this says is, given a recognized state, take that recognized state, go here, take the unique input, and go into a talking state. So that's just going to make sure that every recognized state runs to a talking state next. So by forcing this map to factor through this, I'm forcing every recognized state to update to a talking state.
Can we put an exclamation point in front of the y?
Yeah. Thank you. And the third one is going to say, let's see, I think I want to do the same thing again. A talking state or an unrecognized state. I'm projecting out. I'm only going to look at states that are, so given a talking state, I'm going to say some A letter, and I'm going to return either to its talking state or go back to my unrecognized state. And so my point here is mainly to say that we're going to use, we can use the coproduct structure, the projection maps, things like that to enforce like a pretty good typing system. I mean, it's not like type theory type level in the sense it's not super rigorous, but what I'm saying is like the operations we have available, plus and projection, things like that, are allowing us to kind of enforce the way we're thinking about this just by how we're writing the maps. Yeah, Evan.
But I guess an important difference in this example from the previous ones is that it's not just any polynomial map with the given domain and codomain as a talking DFSA, but one that has this particular way
That's
of
right.
factorizing it and having certain pieces.
That's right. That's right. So Evan's point was one difference between the talking and the regular ordinary deterministic state automaton is these kind of rules I said, which is that the talker should kind of like, when it goes, it can only go from unrecognized to recognized, and then only going from recognized to talking, and only going from talking to unrecognized. And that's not completely determined by the fact that I'm giving a map like this. But if you allowed it to just be a map like this, it would just mean that you could move between those states more freely. Maybe it's not so bad. The point isn't so much to make this a really good definition. The point is to show you that the sort of thing you could have it do, that's generalizing the usual thing by using the poly aspect of it, the fact that we have different modes at different times. Sometimes you're talking and you're not listening, sometimes you're listening, you're not talking. We could let you listen and talk by like having you have like a reduced vocabulary of inputs when you're talking. We can do all the sorts of things that you imagine could happen, you just have to specify them. So thanks for the question. Okay, so let me define a memoryless dynamical system. Oh, this is example 2. A memoryless dynamical system. I'm not defining it, sorry. I'll give you one that you might call memoryless for each function. So suppose you said, I have plus. It's a function from integers times integers to integers. Then I will give you a memoryless dynamical system with that same interface. So you have this AB function. I'll give you an AB Moore machine or dynamical system. And later we will use plus and wiring diagrams to get Fibonacci. Not later today, but next time. So what we'll do is we'll just take S, we'll just let that be B, and we'll say sy to the S to by to the A. Well, that's the same thing as by to the B, because S is B. So what map like this would act like a memoryless dynamical system? Memoryless meaning someone's going to give you a bunch of A's, you give them F of those A's, and don't remember anything about the past. Just keep giving those things. So how do I give this map? What should I do? Well, on the, let's see if maybe I could draw it this way. So I'll give one of these, and this is B, and B, and B, and A. So if someone gives us a B, we'll just output that B. So phi1, this on positions, we'll just have it be the identity from B to B. And then given an A, we could use this B to determine the new B, but I don't want to, otherwise it would be memory full. And so I just want to take F of A, no matter what. That's a memoryless dynamical system. And what if I wanted to, so now let's do 2 prime. I guess I didn't write 2 prime. Oh, this was supposed to be 1 prime here, a talking one. So 2 prime is for partial functions. Given a partial function means not every input gets an output. Given a partial function f, I want a dynamical system that if you ever give it the exception, it just stops running. So I don't know whether that's good or not, but you could do it. So you can go b y to the b plus 1. sorry, by to the b to b y to the a plus 1. So given that, I guess I have to do it this way. B plus 1, y to the b plus 1. The rule is that I must have this be sy to the s. Okay, and then to give this thing, I'll give a map from b plus 1 to the positions of this. Well, the positions of this are b plus 1. And then given a direction there, if it was from b, then I'm ready to accept a new a and get a new b using my function. But if I was in plus 1 and I land here, I don't ever take inputs again, so I'm done. So this would be a dynamical system that is able to just stop forever.
And suppose we were to modify it and say that it just gives the last value.
And yeah, let's say you want to, the question was, what if you want to modify it so it gives the last value? Good question.
Mapping it to by? Looks like.
Yeah.
Plus by.
B plus 1a, given that a that goes there. Okay, I think what I want to do is tell you how to do. It's a good question. I don't know if I can do it off the top of my head. And so either it's homework, or I wanted to tell you about, later I was going to tell you about what I was calling a repeater. So maybe that's, maybe that would help. But you know what I would do? I think, okay, let me solve your problem, solve the problem you gave me, actually. So let's do, the question was, how would you have it output the last b? And this may not be the most efficient solution, but I'm going to use like 2b y to the 2b mapping to b y to the a plus b. And on positions, it's 2b mapping to 2b, so that's fine. And on directions, given the a that's exceptional, I'm going to map to the b state that's in the wrong side. So I've got like two sides, a b that's continuing and a b that's like ready to be done. And when I get my bad a, I'm going to move into the b that's ready to be done, and I'm going to export that there. In fact, that's exactly how I was going to do something that's going to come next. Okay, so let's do 3, which is Turing machines. Now, we're not ready to wire together anything yet. Tomorrow, or Monday, I guess it is, we'll start wiring things together. But today, we'll just have individual things. So a Turing machine consists of a Turing processor and a Turing tape. And they're wired together somehow. And the processor is up to you, and the tape is a fixed dynamical system. So the processor is sy to the s to some polynomial. And that polynomial for Turing machines, what does the processor, so a Turing machine is like this tape with positions. And at every position is written either a 0 or a 1 or a blank. Okay, so a tape, yeah. So this will be of a tape value here would be a map from z to 0, 1 blank, or maybe an alphabet a if you prefer. 0, 1 blank, a function from z to that is a tape. And then they think, in the Turing machine thing, they have like some kind of read head that's got some, that's able to kind of, you're able to read and write to that spot, and you're able to move the read head left and right. Okay, so the commands that the processor is allowed to issue, those are its outputs. And we'll say that it's allowed to issue go left, go right, write a 1, write a 0, or write a blank. Those are the outputs of the processor. And the inputs of the processor are what the tape can tell it, which are 0, 1, or blank. So the Turing machine is just some bunch of states operating on this thing, outputting these commands and inputting what's on the read head. The tape is some dynamical system that we actually specify in advance. And this will be something that takes in, oh, you know what I want to do? Let's define M to be LR. These are movements. Maybe that's annoying, but, and A to be the alphabet 0, 1 blank. So I'm going to just replace this. So its inputs are part of the alphabet, And it's just going to be easier to write them. M plus A. Okay. And so the tape is going to output an element of the alphabet. So given a tape position, so T is going to be that set. And I'm going to actually define this map. Maybe it should be called tau, I don't know. I'm going to actually define this map in a second, but the tape is going to output an alphabet element and then take as input a movement or an alphabet element. So let's define this map. Given a map from Z to A, what do you think the tape should reveal to the processor? Oh, sorry. I need a map to A for phi1 on positions. So any guesses? What should I do to some tape position tau?
Evaluated 0.
I should take tau of 0. Yep. And now I need, for every tau, so given tau, I'm supposed to give, so I gave my tau here in T, and now I get either a movement or an alphabet. I'm supposed to update my tau to a new tau. So I need a map from M plus A to T. So I have some tape tau, some tape position tau, and then what do I do? Let's call this phi sharp sub tau. Maybe tau's a bad word, but maybe I should call it T for tape. T. Okay. So given a T and T, a position, I need a way to take directions, either a movement or an alphabet letter, and get a new tape. What should I do on the, so to give this thing, it's enough to give a map from M to T and a map from A to T. So what would you do if I gave you a movement, L or R? You have your tape T. What should you do?
Shift.
Yep. You should take, so T, an element here is a function from Z to A. So given a position I, I'll go to T of I plus 1. And it might be minus 1. I just don't, it doesn't matter too much. Either, yeah, okay. And given R, I should take a position I and send it to T of I minus 1. Okay, is that good? And then given A, what new tape should what should I put in position I of the new tape?
If it's not 0, then it's whatever it was before.
Yep, if it's not 0,
it's whatever you got.
if I is not 0, then it's T of I. And if I is 0, then I actually do write my new A there. And so this is a Turing machine and Turing tape as dynamical systems. But but that's actually not what a Turing machine is. It's not quite that. It's that with a halt state. So we're not supposed to really land in these things I said we're supposed to land in. We're supposed to land in something slightly bigger. Yeah, question.
Turing machine is like two systems, processor system and a tape system, not one.
Yeah, a Turing machine is a tape system and a processor system that are like bound together somehow.
And we'll talk about that.
And we'll talk about wiring diagrams next time, yeah. And the tape is infinite, and the Turing machine is usually considered to be finite. The set S is usually considered to be finite. Okay, but really I think a processor is supposed to be sy to the S mapping to M plus A. Oops, y to the a plus halt. And for technical reasons, I'm going to allow it to have a little input there. And the tape is supposed to go from ty to the t to, well, why is this so hard to read? To a y to the m plus a plus t. Actually, I need this. I need to do the same sort of trick I did for Spencer's example last time. So this is still a dynamical system. What this is going to do, t is defined to be tapes. And so what this guy is going to do is when, we haven't talked about how they're working together yet, but soon we'll be able to, next time we'll be able to make it so that this guy is sending the tape a command and the tape is sending data here. And what we're going to do is we're going to have our thing, when it sends halt, it's going to switch from the tape as like an active process to a tape that's complete. And when it's complete, it's just going to output itself. So it outputs, here's my final position, the entire tape, and it's done. And we could give this map, but it's exactly the one I gave before. In the sense, oops, sorry, plus halt plus t. So now this tape, when it's in the normal side, so this is like tape like go plus halt t. I should explain this notation. I'll do it in just a second. So when it's in the go phase, it's running this thing, and it's sending out these alphabet letters, and M's and A's are coming in. Possibly a halt comes in. When halt comes in, it goes into the exact same tape position it was before, like the entire tape just gets put over here. And that side is what gets sent out there. Now the notation I'm writing is whenever I have two sets, I write A, B to mean A times B. And a kind of funny trick is to write like, you know, foo, B. Elements of this one are things like A comma B. And so elements of this one are things like foo, B. So it kind of prints this for you in some sense as part of like how you would write a tuple. And so it's kind of just convenient to, people might write these as type constructors if you're coming from a Haskell type point of view. Go would be a type constructor. But you could just think of it as like a one element multiplier that has a string on it. Okay. Any questions about this? How we're using polynomials to give ourselves access to like different modes? Sometimes we're in the mode of running, and sometimes we're in the mode of halting. And so we have this sort of flexibility.
So I was wondering, for each of these kind of examples, you're describing a pretty broad class of polynomial, like a certain shape of polynomial, or a certain shape of morphism of polynomials corresponds to a certain kind of dynamical system. And it seems like for something like more machines, it's just monomials and morphisms of monomials, so that would be clear how to define a category of them. But some of these, as you get more detailed, it's like also like shapes of certain morphisms, you know, to describe what a Turing machine really is. So have you thought about how to describe, you know, the category of Turing machines as sitting inside the poly?
So the question was, when we think about the regular old Moore machines, our right-hand side is a monomial, by to the a, and all the monomials compose. So sy to the s to by to the a, and those all compose. Whereas in this more general one, we just have a p. So instead of going from sy to the s to another monomial, we go from sy to the s to some p. And these seem to compose, and these don't. Well, these compose, but they're really only composing on the right anyway. And so these also compose on the right. We're never really adjusting that one. So yeah. I don't want to spend too much time on this, so I might cut you off unless it's super fast. But in terms of like the category, it's no harder to kind of define a category here than it is to define a category here.
Yeah, I'm talking about something more like the arrow category, so that you have two distinct Moore machines with different, you know, different states,
yeah.
different.
Yeah, the arrow category, yeah.
that kind of
Yeah, so in terms of like allowing yourself to adjust this and this separately, maybe, yes, that's something that we will talk about.
Cool.
Yeah. Okay, I want to do one more example. Well, although I don't. Do I have time? I might have time. Okay, so we're going to go till 5, as usual. So in this machine, I'm just going to go right to 4 prime, because there is no 4. Instead of like adding two, so I guess 4 would be add 2 numbers. And we talked about that in the memoryless thing. But now I want in 4 prime, instead of adding 2 numbers and just kind of memoryless doing that, what I want is my interface to accept 2 numbers. So imagine something that sends out 2 hands, grabs 2 numbers, retracts its ports, thinks for a while, and then spits out a answer. So it's really this plus this plus this. So I want natural numbers squared. Please give me input, plus working y. So this is saying give me no input, I'm working, plus a natural number, I guess, out. Okay. So I wrote down like how we would do this here. So here's a dynamical system. You start in the in state. So S here is, you kind of need to zoom in here, but it says in plus working n squared. So the number of states are 1 plus n squared. So this machine has in and then n squared many more states. And what it does is when it's in the input position, it maps to in. So on the top, I'll write the state, which the world can't see. And on the bottom, I'll write what world can see. The polynomial is, as I wrote over there, in y to the n squared plus working y plus out n y. OK, so in the input state, you say, please give me input. And the user gives 2 numbers. So it grabs the 2 numbers and runs to that state, like 2, 4 or whatever. So it runs to some state. And then it's working. So what it does is it adds to the first and subtracts from the second, therefore keeping the sum the same. And when it gets to the bottom, it will be it'll output that number to the world, and then it will return to the input state. So we could write this down carefully using all of our notation, but it would just be this picture in some sense. So that's the sort of thing we want, or that I want, is to be able to write the whole protocol, or actually things working through time to give answers. Right, yeah. We could add a monitor to this thing. The monitor would say, I want to actually know what your number is. So if you're in the input state, just say you're at 0, and otherwise just tell me the y coordinate. So tell me how long it's going to take till I get a number. So you could do that, and you could do sy to the s to y as a reset. And what this would do is take any state and return you to input. So if someone hit the reset button, it would return you there. And you might be thinking, like, what are these? These are weird. Well, what I'm going to do is using, as Nelson said, we can multiply things. So we already had a map from sy to the s to this kind of crazy polynomial here. And so we can multiply all 3 and get a map sy to the s. If you have a map from sy to the s to 3 different things, you get a map from sy to the s to n y p. And what that'll do is take any state, tell you how long until you get a number, allow you to reset to the input if you want to, and otherwise just keep working until it's done and then spits out the answer. So those are the sorts of polynomial maps, like the sorts of flexibilities and ways you can use times and plus and stuff like that to manipulate polynomials that you already have into more general or other ones. And to end, we have 1 minute left. So what's the answer? How would you take it if I have a p and the directions are changing? They're p sub 1 sometimes and p sub 2 other times. And the world is supposed to give us a bunch of input so we can run. What should you do when the input type is changing? So somehow you're in the world right now, and no matter where you look, the world gives you data of the exact type you need. Like, how does it do this? What? Well, the answer is that it doesn't care where you look. There's already data there, which means that no matter what position you're in, with your eyes looking there or your eyes looking there, your eyes closed or whatever, there already is, the situation you're in is giving you the direction there, or the input. So instead of giving a sequence of inputs, what we're going to give is a sequence of global sections. A global section just means for whatever position you're in, the world kind of picks one input that's sitting there already for you to look at. In other words, it gives you a map from P to Y. So I call a map from P to Y a situation because what it is it's not the input you're getting, it's the world that's already there, the situation you're in, so that no matter where you look, you see something coming in. And this functor, there's a functor, I guess I'm going to take, it's 12 more seconds or something. There's a functor from poly to set up that has an adjoint that is the representable. So I'm not going to talk much about this, maybe next time. But there's a functor called gamma that gives you the set of global sections. And it's a really nice functor. It's not only a left adjoint, but a global section, if you and I were somehow together in a room, just the two of us, and then a situation for the two of us is the same thing as a map from P of 1, my positions, to situations for you, and you're together with a map from your positions to situations for me. So a situation for us too is just a way that your positions become situations for me and my positions become situations for you. So that's the end of today, and we'll resume next time with wiring diagrams. Thank you. Yeah.
So for the Moore machines, if you actually want to run the machine, you get an iterate function that starts with the state and tells you the state that's n fixed later. Is there some generalization of this for an arbitrary machine?
Yeah. I mean, I think that's what I was trying to start the conversation about here. So what you just said, I think, so the question was, are we still rolling, Nelson? Okay. The question was, so I guess this is like the post time. So I guess what does that mean for your viewers? They just quit if they want to or something? I don't know. Okay. So if you had a map s y to the s to b y to the a, that would be something that's inputting a's and outputting b's. And so we think if we had, and we also have a start state. If we had some list of A0, A1, A2, dot, 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 we would define S sub n plus 1 to be update of A n S n, and B n to be readout of S n. And that's all encoded in this thing here, readout, comma, update. It's like a map from S to B and a map from S times A to S. And so that does not, and so from this we get this B1 thing, B1, B2, etc. But if instead, if instead we had these gamma things that I'm erasing, then what we're saying is that the global sections we're allowing are just the straight across ones. No matter what position you're in, no matter what position you may be in right now, I'm going to send you the same A. I'm not paying attention to what B you're outputting. I'm just giving you the same A. So B outputs, we can think of them as positions. They're like positions of some, like they're like what you're revealing to the world. It's like what your voice box is saying. So the outputs of a Moore machine are being generalized to positions. And in this more general picture, we need a map from sy to the s. Given a map from sy to the s to p, I'm not going to be able to turn inputs into outputs. What I'm going to turn is, if I had a sequence of global sections.
Sorry, what's a global section?
One way to say it is it's a map from P to Y.
Oh, I see.
Another way to say it is like for every position you pick a direction.
Okay.
So yeah. the idea, the reason for the word section is it's kind of like a choice of direction for every position. So so a situation like this, for no matter where you look, there is a direction coming in for you there. And so given that data, what we'll define is S sub n plus 1 would be, I mean, if this is gamma n, we know how to get a new state from that. I guess, I don't know, is gamma n applied to S or something?
Gamma n sharp,
Gamma n sharp
applied to whatever we put in,
applied to whatever we put in
so S, to the less 0, or S
phi
minus 1.
of S n applied to the unit that's here, the one that's sitting here, the star.
And
that's
then you
in
got
there.
to be sharp on that thing, right?
Yeah. So we take this thing, we go to our position, we hit it with the direction that's sitting there for us as part of the situation we're in, and we just return that, phi sharp of that.
Yeah, at S,
Phi sharp at Sn of gamma sharp at phi da 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 da. So it's slightly annoying to write down